What are parasitic effects in power converter design? Have you ever wondered why your power converter might not be performing as well as expected? The answer could lie in something called parasitic effects. These are unintended electrical characteristics that can sneak into the design of power converters. Let's break down what these effects are and how they can impact the performance of your DC-DC converter. First, let's talk about parasitic resistance. This is the unwanted resistance that exists in the wires and connections of your converter. Even a tiny amount of resistance can lead to significant power losses, especially in high-current applications. For example, if you have a long wire or a thin conductor, the resistance increases, causing voltage drops and heating. To tackle this, designers often use materials like copper, which has low resistance, and they try to keep wiring lengths short and conductor sizes large. Next up is parasitic inductance. This effect comes from the physical layout of components and wiring in the converter. It can create unwanted inductance that slows down changes in current flow. This can lead to voltage spikes and ringing, which are not good for stability. In DC-DC converters, this is particularly important because it can introduce electromagnetic noise. Parasitic inductance is often found in capacitor leads and inductor windings. Then we have parasitic capacitance. This is the unintended capacitance that occurs between conductive parts in the circuit. It becomes especially relevant in high-voltage and high-frequency converters. For instance, if you are using wide bandgap devices like silicon carbide metal oxide semiconductor field effect transistors, parasitic capacitance can slow down switching speeds and lead to resonances that increase switching losses. These parasitic effects come from various sources, including the packaging of semiconductor devices, the layout of printed circuit boards, and the design of magnetic components. As switching frequencies and power densities increase, which is common in modern DC-DC converters used in renewable energy systems, the impact of these parasitic elements becomes even more noticeable. So, what are the practical implications of these parasitic effects? For one, they can lead to increased switching losses due to distortions in voltage and current. This can reduce the overall efficiency of the converter. Additionally, they can create unwanted electromagnetic interference, which can affect the reliability of the entire system. Designers must carefully select components and lay out their printed circuit boards to minimize these parasitic parameters. Advanced modeling and simulation techniques are often used to predict and address these effects early in the design process. In the world of electrical engineering, managing parasitic effects is essential for ensuring that DC-DC converters operate efficiently and reliably, especially in high-frequency and high-power applications found in power systems and renewable energy contexts. Understanding these effects can lead to better designs and improved performance in your power converters.